Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's easy level puzzle. And take that easiness with a grain of salt, because it's considered easy by the people on the Logic Masters Germany forum, and there's a lot of really smart people there. Today's puzzle is called Boundary Conditions by B Alpha, and here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. We need to draw a path that only moves orthogonally, doesn't branch, doesn't intersect, overlap, or touch itself orthogonally, and whose two ends are in the cells with the stars. So we need to draw a path. It moves only orthogonally. What does that mean? It means it just moves horizontally and vertically. That's it. It doesn't move diagonally. It doesn't branch, so it's one single path. It doesn't split off. It doesn't intersect, overlap, or touch itself orthogonally. So that means it could touch itself diagonally, but it cannot do something like, say, it cannot do something like this and then move off, right? Because that would be considered touching itself orthogonally, which means that you share an edge. And whose two ends are the cells with the stars. So it must go from this cell to this cell. So technically, this could be a path. That would be valid. So we have to draw a path then. There we go. We have region sum lines, where 3x3 box borders divide the path into segments, and all segments must have the same sum. So as an example, if this were the path, then this would be a segment, and this would be a segment, and these two digits must sum up to what that digit is. So we say we had 3 and 4 here. This would then have to be 7, because the digits on the path, the digits on different segments must sum up to the same sum, or all segments have the same sum. And again, the 3x3 box borders divides the path into segments. We have, okay, well, there we go. That's part of the problem. We have yin-yang shading, where the path cells and the non-path cells each form an orthogonally connected region, and every 2x2 area contains cells from both regions. So let's see. Well, the problem is coming up with a yin-yang pattern that doesn't, that is a path. I'm just going to do a normal yin-yang pattern. This is not actually valid for a path because, obviously this branches here. So that's not obviously not going to work. But take this as an example of yin-yang shading, where one region must form a connected, orthogonally connected region, and the other region, which is considered not shaded, must form an orthogonally connected region. Here we have path cells and non-path cells must each form an orthogonally connected region, and every 2x2 area contains cells from both regions. Now, what is an orthogonally connected region? It's a region where you can go from any cell in that region to any other cell in that region just by going through edges, all while staying within the region. So, for example, to get from here to here, you just go along this path here that I highlighted. And you'll go through edges, all while staying within the non-path regions. What's an example of an invalid shading? It would be something like this. Where basically these cells cannot get to the other cells in the path cells region just by going through edges while staying within the region. They have to go through either a corner or go through an edge but exit the region, which is neither of which is allowed for yin-yang shading. So that is an example of yin-yang shading. We have if two cells are separated by a black dot, one is double the other, and they are in different regions. And if two cells are separated by white dots, they are consecutive, and they are in different regions. So we know that these two cells must be in different regions, and this cell must be in different regions than all three of these cells. And let's use examples. If, for example, this was a 2, this would have to be 1 or 4 to make sure that one is double the other. If this were, say, a 6, this would have to be 5 or 7, because these digits must be consecutive. And remember, between every two dots, the digits that are separated are in different regions. And those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. So, since every dot is essentially a boundary, these must all be different regions than this. So we're going to mark the cells on the path as green. We're going to mark the non-cells on the path as blue. So since these are blue, this is a different region than this. Same with this. This is blue because that's green. This must then be green here. Green has to orthogonally connect out to connect to the rest of the greens, and so these are all connected. This is green here, so this must be blue here. We do not branch, and the green path cannot touch itself. Blue has to orthogonally connect out, so this must be blue here. Same with that. That makes this blue here, because it cannot go this way and that way. That would be considered branching. So then it has to go there. It's green. That goes to green there, so that makes that blue. That means to orthogonally connect, the green has to go this way, so this is green. These are both blue. Okay. What else do we have? Okay, so in yin-yang shading, if you ever have a diagonal that is... So two things in yin-yang shading that you can deduce from just basically taking a look at how yin-yang shading works. On the edge of a grid, you can only have 0 or 2 shading changes. And the reason why is, say we tried to have more than that. If we tried to have more shading changes, so say we try to go blue and then let's do the minimum, 4 shading. First of all, you can't have odd numbers of shading changes, right? If you change one shade, it has to necessarily change back to the other shade eventually, right? Because just by the, process, right? So if it changes shade here, it can't go suddenly all the way green around here and then how does it can't change back, has to change back eventually. So that's why you always have an even number of shading changes in yin-yang shading. On the edge of a grid. Also, if you have a diagonal that is the same shade, the other diagonal cannot be the same shade, whether it's blue or it's matching shade or it's the opposite shade. And the reason why it can't be a matching shade is obviously you have a 2x2 area which does not contain the other region. And every 2x2 area contains cells from both regions. Oh, I forgot to use that as an example. Anyways. Um, what happens if you try to make it the opposite shading? Well, if you try to orthogonally connect the two regions on the opposite of the diagonal, that will necessarily break apart the other region into two separate regions when it's supposed to be one fully orthogonally connected region. Same thing occurs if you try to orthogonally connect the blues. You'll break apart the greens into two separate regions, which is not allowed. And those are the two main deductions you have for yin-yang shading. Well, we've already changed shades twice on the edge of the grid, so that means we cannot have another change of shading on the rest of the edge of the grid. So these must all be blue. Green has to orthogonally connect out, so it must go out this way. This must be green because it's different from, actually we have a 2x2 area that's all blue here, and a 2x2 area that's all blue here. So this must be green, this must be green. So this must, as a path, enter and exit this way. We have a 2x2 area that has 3 green, so this can't be green. This is going to be the same, 2 green, entering, and a blue. The green has to enter and exit as long as it's not part of the star area. So then this is blue, this is blue. The green has to orthogonally connect out and connects that way, so it has to go there and there. That means this is the path here. So we cannot, the path cannot touch itself orthogonally, so therefore it cannot do something like that. This exits out that way, this exits out that way, this can't go to the right because, again, we know there's a boundary there between these two cells, so it must go that way. This can't enter a path and then exit back out, so this must be blue. One of these is green, and then one is blue. If we try to make this green and that blue, we'd have a diagonal here of green. That would be blue, and therefore, by the deduction I made, you can't have a diagonal of the same. You can't have two diagonals which are the same set, no matter what. This would have to be green, but then it would branch by going that way. So this cannot be green here, which makes that blue. So this must go green here, which means this does not connect. This cannot branch, so this is blue there. Therefore, this must go up in green and it connects out orthogonally. Same with this. We can't go this way because then that would be touching itself. Because you can't just form a full circle here, and this path has to start here and then end there. So this must be blue there. One of these is green and one of these is blue. If this were, well, it could be green either way, so that's fine. This has to orthogonally connect out again because it can't go this way because that would be touching itself there. Therefore, these can't be green because that would be considered branching. Okay, and this must form, again, this path is a region sumline. So, we know these 3 digits must sum up to the same as these 4, which sums to the same sum as these 3, which sums to the same sum as these 2 and these 2. Let's try to figure what this is. This digit is next to 2 unique digits on a whisper, not a whisper 5, on a Kropki dot. So it's in a 1-to-2 ratio with 2 unique digits. The only 2 digits that satisfy that are 2, which is in a 1-to-2 ratio with 1 and 4, and 4, which is in a 1-to-2 ratio with 2 and 8. So this has to be 2 or 4 here. This is 1, 2, 4, 8 here, 1, 2, 4, 8 here, but this digit is consecutive with 2 other digits. 1 doesn't satisfy that. So this must be 2, 4, or 8 here. If this is 2, this would be 4, this would be 1, 3 as a pair. So that's potentially possible. If this is 4, this would have to be 3, 5 as a pair, and if this is 8, this is 7, 9 as a pair. So 2 can go to 4 here and then 8. 4 could go 2 down to 1. And then 8 could go down to 4, which is then 2. So those are the possibilities. Now we have a guaranteed 2 or 4. That is going to be next to one of these black crocky dots. Because if you have 2, which is in 1 to 2 ratio, it's 1 to 2 ratio with 1 and 4. If you have a 4 there, then that's going to be in a 1 to 2 ratio with 2 and 8. So we're guaranteed 2 and 4 in this box. 4 has to be one of these two. And this must be 2 in one of these 3 cells here. Therefore, this pair of digits in 1 to 2 ratio cannot contain 2 or 4. If it's 2 and without 2 or 4, the only pair of digits that are in a 1 to 2 ratio, you eliminate 1, 2, 2, 4, and 4, 8, so you have 3, 6 left. So this must be a 3, 6 pair, which eliminates 3 and 6 in the rest of the box, so this can't be 3 or 6. Which means 2 cannot be here, because if this is 2, it would have to be consecutive with 1 and 3, but 3 is not available because of the 3, 6 pair in the box. So this can't be 1, and this can't be 2 here. 4 can't be here for the same reasoning. If this is 4, this would then be 5 and 3 and 5 consecutive with it, but we have a 3, 6 pair in the box already, so this can't be 4, which means this is 8, which is in consecutive with 7 or 9. That leaves this as 4 to be in a 1 to 2 ratio with the 8, and 2 to be in a 1 to 2 ratio with the 4. So, these 3 digits sum up to the same sum as these sets here. But this is 2 digits adding up to that sum, and this is 2 digits adding up to that sum. Well, if we have, and they're in the same box, if we have this be 8, 2, and 6, that's 16. And only 2 digits can ever add up to 16 if they're unique, which would be 7 and 9. And we can't have both of these be 7, 9 pairs because that would be duplicated in the box. So this can't be 6, it must be 3, which makes that 6. So these must add up to 13 for the region sum lines. Okay. This is in a 1 to 2 ratio and cannot contain 2 or 4, so it must be a 3, 6 pair. That means this can't be a 3, 6 pair, because neither this digit cannot be 3 or 6. The digits that are next to black quapkey dots can never be 5, 7, or 9. Because 5, 7, or 9, if you have them, you get 2.5, 3.5, 4.5. If you double them, you get 10, 14, or 18, none of which are digits. So this has to be 1 or 8 here, which makes this 2 or 4 there. This cannot be 3 and 6, so this must be the other digits that are 1, 2, and 4, or 8. Because 3 or 6 are not possibilities here because of the 6 in the column. So we have a 1, 2, 4, 8 quadruplet in box 9. That eliminates 1, 2, 4, 8 in the rest of the box. So we are left with 3, 5, 6, 7, 9. And this can't be 6 because of 6 in the column. No 3 here because of 3 in the column. And again, this must add up to 18. Sorry, 13. 8, 3, and 2 add up to 13. These 4 must add up to 13. And it cannot have 3 and 6. It could be 3 or 6, though. It has to have 1 out of 3 or 6. Remaining digits in box 3 are 1 and 5. This can't be 3 or 6 because of the 3, 6 pair in the column. Where is the 3 in box 9? Cannot be here or here or here, so it must be here. So that's 3, and one of these is guaranteed to be 6. Remaining digits of column 9, we have 1, 5, 7, 8, 9 as possibilities. Can we ever have 9 here? The answer is no. Actually, we can't even have 8 here. So 4 digits adding up to 13. 8 and 1, 2, 3 already add up to 14, which is too large. So that's a minimum. So this cannot be 8 or 9. So we could have 1, 2, 3, 7. 1, 2, 4, 6. Or 1, 3, 4, 5. 2, 3, 4, 5 is too big. That adds up to 14. So again, 1, 2, 3, 7. So it could be 3 there and 1, 7. 1, 2, 7, I should say. 1, 2, 4, 6. So in that case, if this was 1 and 6, this would be 2, 4 as a pair, but that would eliminate all possibilities for that cell. So that's not possible. And then the last one is 1, 3, 4, 5. So this is 1, 4, or 5 there. And either way, 3 has to be part of the set, adding up to 13. So this must be 3. That means this can't be 3 here. It's 6. And this has to be 2 or 4, right? Because it can't be 2 or 4 there. One of these is 2 or 4 because it's either 1, 2, 3, 7 or 1, 3, 4, 5. And this is 2 or 4, which means we can't have another 2 or 4 in this column. Okay. We have 3 digits here adding up to 13. Can we have 9? The answer is no, because 9 only adds up to, with 2 other digits to add up to 13 with 1 and 3. So no 9 here. So the only way these add up to an even odd sum is if this is 1. And that would be, this is 1, which makes that in a 1 to 2 ratio with 2, and that would force this to be 4, 8. So you'd have 1 and 4 here to add up to an odd sum, which makes that has to be even then to add up to an odd sum of 13. But 1, 4, and 6 only adds up to 11, which is not the sum for the region sum line. So this cannot be 1 here. So these are both even, and it must add up to, with the 5 or 7, to add up to the odd sum of 13. So 8 would guarantee this is 2. So that doesn't work, because 8 and 2 is 10, plus 3 would have to add up to 13, but that doesn't work. So this cannot be 8 here. Therefore, this is a 2, 4 pair, which eliminates 2, 4 in the rest of the box. So this is a 1, 8 pair there. And 2 and 4 plus 7 adds up to 13. So this is 7, which eliminates 7 in the rest of the box. That means this can't be the 7 here. Eliminates 7 in the rest of the box. We have a 5, 9 pair in box 9, which eliminates 5 and 9 in the rest of the box. So no 5 or 9 there, it's 6. This 5, 9 pair eliminates 5 and 9 in the rest of the column, so no 5 or 9 there. It's 1, which makes it not 1, so it's 5. 1 and 5 eliminate 1 and 5 here, so it's 7. So 3 and 7 is 10, which means this must be a 1, 2 pair. That eliminates, and 7 eliminates 7 here, so that's 9, which eliminates 9 there, so it's 7. 1, 2 as a pair eliminates 1 and 2 in the rest of the column, so no 2 there. It's 4, which is in a 1 to 2 ratio with 8. 8 eliminates 8 there, so it's 1 and 2 there. Remaining digit of column 8 is a 5. Remaining digits of column 7 are 4, 8, and 9. We have 2 digits here adding up to 13. The possibilities are 4, 9, 5, 8, and 6, 7. And it's the same with this. So we have 4, 9, 5, 8, or 6, 7 there. 4 and 8 can't be in these digits because of 4, 8 in the row. That eliminates 9 here and 5 here as possibilities. 7 cannot be here because of 7's in the row. That eliminates 6 here as possibilities. So this is 5, 7, or 9, which is consecutive only with even digits. And that would be 4, 6, and 8 specifically, but this can't be 4, 8 because of 4, 8 in the row. So this can't be 4, 8 as an even digit. To be consecutive, it must be 6, which means this has to be 5 or 7 to be consecutive with it, but this can't be 4 anymore. And 6 eliminates 6 in the rest of this box, so this is 8, which adds up to 13 with 5. That means this can't be 5 and 8, it can't be 6 and 7, it must be 9 and 4 there. Remaining digits of row 7 are 2, 3, and 7. This is in a 1 to 2 ratio. This is in a 1 to 2 ratio without 4 or 8 available. So it's 1, 2, 3, or 6 as possibilities. Remaining digits of row 8. We have 1, 3, 5, 6, and 9. This can't be 5, 6, or 9 because of 5, 6, or 9 in the box. And where is 3 in this box? Can't be here because of 3 in the row, so it has to be here. And this can't be 3 then. Remaining digits of box 8, we have 1, 2, and 7. This is in a 1 to 2 ratio. It can be 1, 2, 2, 4, or 4, 8. It cannot be 3, 6 because of 3 and 6 in the column. These digits are consecutive and cannot contain 4, 8, or 7. So you could have 2 with 1 or 3, and this can't be 3 because of 3 in the column. You could have 5 and 6, as long as this is 6 and that's 5. And we don't have 7, 8, so 9 is not possible. So these are the only possibilities. Okay. This must sum up to... Oh. What we cannot have... So if we try going this way, that would be 5 digits trying to add up to 13. And they must all be unique because they are in the same box, but therefore that's a minimum of 1, 2, 3, 4, 5, which adds up to 15, which is too great for the sum for this region's sum line. So this cannot go up here. It must connect that way. Therefore, this is blue. These must be blue. We cannot have 2 by 2 areas that are all blue, so if it connects that way, these would be 2 by 2 areas that are all blue. So it must be green here, green here. This is blue because we can't branch on this path. Therefore, we connect there and there. So this must be 2 digits adding up to 13, and same with this. And the only possible combination here would be 6 and 7. Because 1, 2, and 3 can't add up with another single digit to add up to 13. So this is 6. That makes that 7. 6 is consecutive with 5 out of those digits. That eliminates 3, 6 as a pair in the rest of this row for the 1, 2 pair, or 1 to 2 ratio. This must be 2 digits adding up to 13, and we don't have 5 available and no 6 or 7. So that just leaves 4 or 9, which means this must be 4 here, and this must be 9 here. We have 3 digits here adding up to 13, and these 3 digits must add up to 13. That's 26. 7 eliminates 7 here. Remaining digit in row 2 has to be a 3. So we have, this adds up to 13. It's either 1, 3, and 9, or 2, 3, and 8. Oh. 3 eliminates 3 in the rest of the column. Oh, my eyes are getting bothered by this. Okay. So this is the path. It does form on a yin-yang shading. Remaining digits of row 3. We have 1, 5, 8, and 9 available. No 5 here, or 9 here because of 5 and 9 in the box. And where is 1 in box 2? Cannot be here because of 1 in the row, so it's just left here. So this is 1 that eliminates 1 in the rest of the row. 1 eliminates 1 as a possibility here and here. So this is either 2, 4 or 4, 8, with the guaranteed 4 being in one of those two cells. Remaining digits of column 5. We need a 9 somewhere. It has to be here, though. So again, 9 adds up only with 1 and 3 to add up to 13 if it's 2 other unique digits. So this must be a 1, 3 pair. That eliminates 9 in the rest of this row and 1 and 3, which means the remaining digits in row 4 have to be 2, 4, 6, and 8. Interesting. Remaining digits of box 2 are 2, 3, and 8. This can't be 3 because of 3 in the column. We now have a 2, 4, 8 triplet in column 5, which eliminates 2, 4, and 8 in the rest of the column. So this can't be 2, it's 7. No 7 here. 8 eliminates 8 as a possibility here. So these three digits add up to 13 also. And without 1, 3, or 9, or 6 available. So we know 6 has to be one of these 3 digits. Can't be here or here because of 6 in the column, so 6 has to be here. 7 cannot be here, or these two cells, so it must be here. So 7 plus 13 minus 7 is 6. So this must be 2 and 4. And this can't be 4, so this must be 4 there. That's 2. That 4 is in a 1-2 ratio only with 8 because 2 is here, so that leaves that as 5. 2 eliminates 2 here, so it's 1 and 2. 8 eliminates 8 here, and 4 eliminates 4 there. Okay. Remaining digits of row 5. We have 1, 4, 7, 9. Row 6, we have 3, 5, 8, 9. No 3 here because of 3 in the column. Remaining digits of row 9. Actually, let's do row 1. We have 4, 6, and 7. Now row 9, we have 4, 5, 8, and 9. So then we just have to figure out these sums adding up to 13. We have a guaranteed 1 in one of these 3 cells. We have a guaranteed 6 in one of these 3 cells. Can we have both 1 and 6 here? The answer is no, because 1 and 6 to add up to 13 with another digit would have to be a 6. 1, 6, and 6, and we can't have repeats in boxes. So this is guaranteed to be 1 out of 1 or 6, and this has to have 1 out of 1 or 6 only. You could have 1, 5 doesn't work. 1 and 5 add up to 6, but requires... Actually, it does work. 1, 5, and 7 work. Oh. 1, 9, and 3 works. And then 6, 5, and 2 works. Great. So all of them work. Huh. Okay. What about these sets of three? Um, huh. Um, we know this is either 1, 9 or 2, 8 here. Um, we don't know anything else. Uh, so again, the possibilities are 1, 5, 7. Um, 1, 6. It can't be 1, 6. 1, 9, 3 or 5, 6, 2. It's quite a variety. What about these three? Can we ever have 9? Okay, so this is an even sum. So that means the rest of the sum must be odd, because to add up to an odd sum, you must be a sum of even and odd digit. And this is guaranteed to be even because we have 1, 3, 5, 7, 9 already counted for in that row. So one of these is odd, which means the other one has to be even. Um, huh. Where's the 3 in column 2? It's either here or here. Which means either this must be 3 or this must be 3. If this is 3, it has to have 2 evens here. So then it must be 4 and 6 to make that work. If this is 3, then it has to be 1 and 9 as a pair here. So then this would be 2 or 8. Because it can't be 1, 9 because that would eliminate all possibilities for that cell. And then this would have to be a 6 or a 4. Well, we know we have 2 evens here and an odd. Um, wait. Yeah, it has to be 3, 4, 6 if that's the case. Um, can this ever be 4? I guess you could have 4, 1, 8. Can you ever have 2 here? Or 8. If we have 8 here, that makes this 1, 9. And then to add up to 13, 8, it'd have to be 2 and 3. But this can't be 2 or 3 here. So this cannot be 8 here. If this is 8, you'd have the same problem, right? It has to be 2 and it would be 1, 9 there. So to add up to 5, which you need to add up with the 8 to add up to 13, it would be 2 and 3 here, but this can't be 2 or 3, so this can't be 8. Can we have 2 here? If we have 2, again, this becomes 1, 9. So the other 2 digits would have to add up to 11. Can't be 3 and 8. No 2 and 9. 4 and 7 is not possible, and 5 and 6 is not possible. So the answer is no, this can't be 2. So this is guaranteed to be 4 or 6 here. So 6 works if this is 4 and 3. That's fine. If this is 4, okay, so these are already guaranteed to be, if this is 4, these would have to both be odd, which does not add up to an odd sum. it adds up to an even sum. Because we have two odds, therefore they must add up to an even, and plus an even, it gives you an even sum. So if this is 4, that's not going to work, which means this has to be 6. That eliminates 6 in the rest of the box and column. That means these twos must add up to 13 minus 6, which is 7. So no 9 here. This is odd, so this must be the even here, so that's 4, which means this is 4 and 3 there. That eliminates 4 in the rest of this row, so it's 9, which eliminates 9 here, so that's 8, which eliminates 8 there, so it's 4. No more 4s here, no more 4s or 9s here, and no more 3 or 8 here. 3 eliminates 3 here, and 4 in the rest of the column. 4 and 6 eliminate 4 and 6 here, so it's 7. That eliminates 7 in the rest of the column, so that's 2, which makes this 7. That makes that 3. 2 eliminates 2 here, so it's 1 and 2. 2 eliminates 2 here, so it's 8 and 2 there. 1 and 9 add up to 10 with the 3. That adds up to 13. 2 has to be with 5 and 6 here, so this is 5, that's 6. And that leaves an 8 there. 5 eliminates 5 here, so it's 9 and 5. 6 eliminates 6 here, so it's 1. 2 eliminates 2 here, so that's 1 and 2. 1 eliminates 1 here, so it's 3 and 1. 2 eliminates 2 here, so it's 3. No 8 here because of 8 in the column, so that's 2. This can't be 2 or 3, it's 8. 1 eliminates 1 here, so it's 7 and 1. 9 and 8 eliminate 9 and 8 here, so it's 5, which makes that an 8. 5 eliminates 5 here, so it's 9 and 5. 6 and 7 eliminate 6 and 7 there, so it's 4, which makes that a 6 there. That leaves us a 4 here and a 9 here. And that's the solution. Yeah, I guess easy is fine. It never was that difficult trying to figure this out, but I have a little reservation though with the yin-yang shading. If you're not used to it, maybe you get like kind of confused about how to solve this. They're all things you can derive, or deduce, I guess I should say. Derive is, yeah. But interesting. It was a fun puzzle. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.